So let's get started from where we stopped. So we started, if you just recall, we started from plane wall. So where we said that the temperature is varying along the space and also time. So that's why we had a temperature variation term with space and the temperature variation term with time in the heat diffusion equation. And this was the initial condition, and this is the convective boundary condition, and this is the symmetric boundary condition. Symmetric boundary condition, and we try to non-dimensionalize this. Now we try to non-dimensionalize, and what are the advantages of that non-dimensionalization? How does the non-dimensional equation look like? Let us write that. So our equation was del squared t by del x squared equal to 1 by alpha dou t by dou t, when non-dimensionalized, reduced to dou squared theta by dou x squared equal to dou theta by dou Fourier number. What was theta? Theta of x comma t equal to t of x comma t minus t infinity divided by ti minus t infinity, and capital X equal to small x by capital L, and Fourier number is alpha t by L squared, and Biot number is HL by K. Remember, this L is the thickness of the half thickness of the wall, okay. So not the characteristic length here for this case. So T of x comma 0 is equal to Ti, this is the initial condition. Now theta of x comma 0 is equal to 1, which is what we got, and dou t by dou x at x equal to 0 is 0, and here dou theta by dou x at x equal to 0 is 0. So minus k dou t by dou x at x equal to L is equal to h into t of L comma t minus t infinity reduces to dou theta by dou x, capital X, at x equal to 1 equal to minus Biot number into theta at 1 comma Fourier number. So what is the beauty? Why did we do this? Why did we do this non-dimensionalization? Because the temperature, if you just take, the temperature is a function of heat transfer x, it's a function of x, it's a function of x, it's a function of t, time, thermal conductivity, heat transfer coefficient, thickness of the wall, alpha, that is thermal diffusivity, so Ti, initial temperature, T infinity, so many parameters. But now if you reduce, theta now is only a function of capital X, Biot number and Fourier number. So my temperature distribution is more generic when I get the temperature distribution in terms of theta. So now the next question is, what is the physical significance? Before we move on to the plane wall and try to solve the problem, what is the physical significance of Fourier number? Physical significance of Fourier number. Physical significance of Fourier number. Fourier number is equal to alpha t by L squared. So I can rewrite this as k L squared. Remember, alpha is k by rho Cp. So k L squared delta t by L divided by rho Cp L cube delta t by t. I have just done nothing, multiplied and divided it by delta t and multiplied and divided it by L. Okay. So when I do that, so this is nothing but the q dot conducted within the body. And what is this? Rho, this is nothing but rho v Cp dot T by dot T. This is q dot stored. Q dot stored. So it is, that is, if you are to show this in the form of a beautiful figure, you can see that the q dot, whatever you are giving, is how much of that is actually getting stored, how much is getting stored within the body compared to how much is getting conducted. If the Fourier number is very high, means that q conducted is more than what it is stored, and if the Fourier number is low, means it is storing more compared to that of q conducted. So that is what is the physical significance of this Fourier number. Now what really constitutes this is an infinitely large plate. I am taking first large plate. Actually, after the large plate we shall take up the cylinder and also the sphere, but right now we are in a large plane wall. Large plane wall, when I say that, it only means that the thickness of the wall is small compared to height and width of the plane wall. If you just take the wall of your room, that would satisfy this condition. So that is what we will. Now the question is how to get this temperature distribution mathematically. Without proof, we are going to give you the solution of this temperature distribution for a plane wall. So what is that exact solution for a plane wall is our next question. So the exact solution of for a plane wall, for a plane wall, okay, that is theta. This is without derivation I am giving. At in advanced courses you will get this derivation. If you are interested, you can email us, I can supply this. T of x comma t minus t infinity divided by Ti minus T infinity is given by sigma of n equal to 1 to infinity a n e to the power of minus lambda n squared Fourier number cos of lambda n x by n. And what is a n? Fourier number, you know, Fourier number is nothing but alpha t by L squared. And now what is a n? A n is 4 sine lambda n upon 2 lambda n plus sine of 2 lambda n. Now who gives me lambda n? Lambda n is obtained if you know the Biot number. You will be knowing the Biot number for your problem. So lambda n tan of lambda n. This is a and what is the definition of the Biot number? Biot number is H L by K. K is the thermal conductivity of the plane wall. Now this is what is called as transcendental equation, and this will have transcendental equation, and this will have multiple roots. So we do not have to get these roots, they are all given as a table. So if you really see, for a given Biot number, you can see that there are multiple roots, but in this table I am just giving you lambda 1, lambda 2, lambda 3, lambda 4. So if you know the Biot number, you can get these roots, and once you get these roots, once you get the lambda n, you can go back and calculate the a n using this relation, and once you get a n at any Fourier number at a given location x, you can use this series. It is a series solution. Next question is, how many terms of this series I am supposed to take? That is, how many terms I have to take to get the correct solution. Fortuitously or luckily, This is for different Biot numbers I have given. So luckily what happens is that for a Fourier number of greater than 0.2, for a Fourier number greater than 0.2, luckily if the Fourier number is greater than 0.2, one term is first term of the series is would suffice. First term would suffice. In that case, what will happen for a plane wall? Theta of x comma t is equal to t of x comma t minus t infinity divided by ti minus t infinity is equal to a1 e to the power of minus lambda 1 squared Fourier number cos of lambda 1 x by L. So one term is sufficient to solve the problem. Okay. So now incidentally there is a table, you do not want to calculate A1 also using this complicated equation. So we are giving you a table, where in which for a plane wall, for example you see here for a plane wall this is the Biot number, and for a plane wall for a given Biot number, for getting only the one term series you can get lambda 1 and A1. So Biot number you will calculate using HL by K, plane wall of thickness 2L, and you will substitute that A1 and lambda 1 at any given location x at any time t, Fourier number equal to alpha t by L squared. You can compute the temperature at any given x comma t for a given Ti and T infinity. So that is what we are going to do. We will solve a problem so that you will become comfortable with this methodology, and then we will take up cylinder and sphere and we will solve a problem as well. Okay. So at the center of the plane wall, what will happen? At the center of the plane wall, that is, if you take up at x equal to 0, what will happen? At x equal to 0, so cos of 0 will become 1. So you will have only theta at 0 comma t will be equal to a1 e to the power of minus lambda 1 squared Fourier number. If you really closely see this equation, if you recall, for lumped body the temperature varied exponentially, that is continuing here. This cos lambda, this is the time varying parameter. Time variation is captured here with this term, and the space variation is captured with this term. So the time variation continues to be exponential and space variation is varying with cos of lambda 1 x by L. Okay. So with this exact solution for temperature, now the next question would be, what is the total energy transferred? Total energy transferred from the wall. That is the next question. From the wall, that is delta EST, that is the energy stored. That is nothing but, this is nothing but Q equal to rho VCP, that is rho Cp temperature variation, that is T at x comma t minus of Ti into dV, okay, at any given instant of time. Remember, this is dV, so this should be triple integral. Okay. So the integration is performed, integration is performed over the volume of the wall, and here the negative sign, in case if you end up with negative sign implies that heat is leaving the body. Okay. So just to get you acclimatized with what I am saying is that, so my body was at Ti and which is having rho Vcp and it is exposed to h comma t infinity, and what is the maximum q dot one can have, what is the maximum q dot is for a time t tending to infinity, my temperature will become T infinity, the temperature of the body will reach the fluid temperature eventually after time T infinity. So that is the maximum heat transfer I can get. So but the actual heat transfer is obtained by integrating. So the maximum heat transfer is Q maximum is mCp T infinity minus Ti, that is my body has reached T infinity. So rho Vcp Q maximum equal to T infinity minus Ti. So Q maximum equal to rho Vcp T infinity minus Ti. Now without derivation, like temperature distribution, I am going to give you the relation Q by Q max is equal to 1 minus theta naught wall, that is for plane wall, into sine of lambda 1 divided by lambda 1. I have taken only the first term series, and if you recall, theta naught wall was equal to A1 e to the power of minus lambda 1 squared into Fourier number. Okay. So this is fetches you what is the total energy transferred from the wall. Okay. So this is what it will get you. So what is that we got? Let me just recall what is that we got. We just started with the plane wall and we non-dimensionalized this equation and got this as a function of Biot number, Fourier number and x. Without doing maths, we stated, without solving the PDE, that is the partial differential equation, we gave you the solution where the temperature is a function of Fourier number and also the location, that is the time and location. So here we have gotten the, for a given Biot number, you can get the lambda 1, lambda 2, lambda 3, lambda 4, and we said that if the Fourier number is greater than 0.2, one term is sufficient. So for a given Biot number, from the table you will get lambda 1 and A1 and Biot number being HL by K. So and after that we went to energy transferred and we got the relation for energy transferred for the plane wall as Q by Q max for the wall equal to 1 minus theta naught wall sine lambda 1 by lambda 1. So Fourier number of 0.2, the infinite series solution can be approximated only by first term. So what we will do now is that we will solve a problem and then we will see how to get acclimatized with this problem. That is, in the problem what we are taking here is that in the problem, so there is a plane wall, it is a simple plane wall. So let me explain you this problem. It is a simple plane wall, actually it is a pipe. Okay, let me read that problem and then we will come back. Okay, consider a steel pipeline that is 1 meter in diameter and having a wall thickness of 40 mm. The pipe is heavily insulated on the outside and before the initiation of the flow, the wall of the pipe are at uniform temperature. You may be thinking that this is a cylinder, but how can I use plane wall? I am going to make an approximation that the thickness 40 mm is very small compared to 1 meter diameter. So the curvature effect can be neglected and the pipe wall can be considered as a plane wall. Let me repeat. The plane wall of the pipe wall is considered as a plane wall because the wall thickness is very small compared to the diameter hence the curvature effects are neglected and assumed this as a plane wall. And the rest is, it is the walls of the pipe are at a uniform temperature before, that is Ti is 20 degrees Celsius. With the initiation of the flow, the hot oil at 60 degrees Celsius, that is T infinity is 60 degrees Celsius, is flowing with a convective condition, that is H equal to 50 watt per meter squared Kelvin, which is quite high. So now question is, what are the appropriate Biot and Fourier numbers at 8th minute after the initiation of the flow, and at 8th minute what is the temperature at the exterior pipe surface covered by the insulation, that is at x equal to L, what is the pipe surface temperature, and what is the heat flux to the pipe from the oil at T equal to 8th minute, and how much is the energy per meter of the pipe length has been transferred from the oil to the pipe at 8th minute. So this is the plane wall. Let me write this. So let's take up and let's solve this problem. So that is, you have a plane wall, okay, this side you have insulated, and one side you have put the convective boundary condition H equal to 500 watt per meter squared Kelvin, and T infinity is 60 degree Celsius, and this is Ti is at minus 20 degrees Celsius. Ti is at minus 20 degrees Celsius, and this length L equal to 40 mm. Now you might be wondering that we solved for a plane wall with at the center, and this was x equal to L. We have the solution for this case where you have h comma t infinity and h comma t infinity. But is this case similar to this case? Yes, because if it is insulated at this condition, dou t by dou x, okay, at x equal to 0 will be 0 because there is no heat transfer rate. So it is insulated, that is why. So this solution of what we had here, also we had taken dou t by dou x by symmetry, dou t by dou x at x equal to 0 as 0. So both are same, both are same. So that is why I can apply this solution to this case. Now I need properties. At what temperature I should be taking? I should be taking the properties at average of minus 20 plus 60 divided by 2, that is at 20 degrees Celsius or 293 Kelvin. So if you take the properties here at this temperature, so you get rho equal to 7832 kg per meter cube, and Cp is 434 joule per kg Kelvin, and alpha, that is K by rho Cp, is 18.8 into 10 to the power of minus 6 meter squared per second. Now the first thing is I need to check what is now time at t equal to 8 minutes. What is the Biot number? If the Biot number is very less, I can consider this as lumped, but let us just check. Biot number is HL by K. H is what is given to be 500, L is given to be 40 mm, that is 40 into 10 to the power of minus 3. Thermal conductivity is found to be, the thermal conductivity is given to be 63.9 watt per meter Kelvin. So 63.9, so you get a Biot number of 0.313, which is greater than 0.1, which is greater than 0.1, so not lumped at all. So I have to take the spatial variation, it is not lumped. Now at 8th minute, what is the Fourier number? Alpha t by L squared. Alpha is 18.8 into 10 to the power of minus 6. 8th minute 8 into 60 divided by 40 into 10 to the power of minus 3 squared. So Fourier number I get as 5.64. So this Fourier number is indeed greater than 0.2. So one term solution is good enough for me. Okay. So if that is the case, my solution, first question is at the center of the plane wall, what is the temperature distribution? So at the center of the temperature distribution, that is theta 0 comma t, that is T of 0 comma t minus T infinity divided by Ti minus T infinity equal to A1 e to the power of minus lambda 1 squared Fourier number. Now for a Biot number of 0.313, I need to get A1 and lambda 1 from table. So let us go back to the table. If you go to the table, here is the table, here is the table. So in this table, so we have the Biot number, my Biot number is 0.313, and here at 0.3 I have and 0.4 I have. I have to interpolate between these two. I will show for one how to do the interpolation. So at 0.3 it is 0.5218 and at 0.4 it is 0.5932 lambda 1. So at A1 is 1.045 and 1.058. So let us see how do we do this interpolation and get the values. That is, you have at Biot number 0.3, you have a lambda 1 as 0.5218, A1 as 1.045, at 0.4 you have 0.5932 and this is 1.058. So for interpolation, so for lambda 1 is equal to 0.5218 plus 0.5932 minus 0.5218 divided by 0.4 minus 0.3 into 0.5 into this is into 0.313 minus 0.3. This will fetch you of a lambda 1 of 0.531. I just did the interpolation. Similarly, for A1, you can write this as 1.045 plus 1.058 minus 1.045 divided by 0.4 minus 0.3 into 0.313 minus 0.3. So you get A1 equal to 1.047. So substituting this, that is, this implies that t at 0 comma t minus t infinity is 60 divided by minus 20 minus 60 equal to A1 is 1.047 e to the power of minus 0.531 squared into Fourier number. The Fourier number, we know that it is, we have calculated 5.64 for the 8th minute, it is 5.64. If you just do this pressing the calculator, you get t at 0 comma 8 minute is equal to 42.9 degree Celsius. So it got heated up from minus 20 degree Celsius to 42.9 degree Celsius in 8 minutes at the exterior of the wall, that is at x equal to 0. At x equal to 0, so you have, that is at the insulated condition, that is at here at the insulated condition, you are getting the 42.9 degree Celsius. So in the next class, what we will do is, we shall continue this problem and solve the rest of the, that is the heat transfer rate and the energy stored, we shall solve in the next class. Thank you.